This is our presentation about predicting airline arrival delays using machine learning. Airline delays remain a major issue in the aviation industry, and these delays impact passenger satisfaction, airline operations, and airport logistics. The project uses machine learning to predict flight arrival delays. The goal is to provide actionable insights for airlines, airports, and passengers. Three models were applied to continuous data: multiple linear regression, random forest, and k-nearest neighbor.
Flight delays are a persistent issue in the aviation industry with substantial economic, operational, and customer service implications. According to the FAA, flight delays cost airlines approximately $22 billion annually, encompassing increased operational expenses and other related costs. The Joint Economic Committee's 2008 report highlighted that the domestic passenger flights were delayed by more than 1.8 million total hours, leading to significant economic impacts.
This study explores the use of various machine learning algorithms to analyze historical flight data and identify patterns influencing delay occurrences. By comparing the performance of these models, this research aims to assess their predictive capabilities and provide insights into which methodologies are well suited for predicting future delays in the airline industry.
The data set we had 17 predictor data columns, 5 of which were categorical, 12 were numerical. Each of the columns had 433 samples. To pre-process the data, we started by cleaning it. We removed all columns except for the flight number, origin airport, scheduled elapsed flight time, and actual elapsed flight time, and all other columns were removed due to redundancy or irrelevancy. For encoding, the origin airport data column was encoded to convert it to numerical values for ease of analysis.
So for our analysis, we went with 3 different models: the multiple linear regression model, random forest model, and k-nearest neighbor model. For the multiple linear regression, the model takes the relationship between a dependent variable and 2 or more independent variables by fitting them into a linear equation. This model assumes the normal distribution, and to analyze this model, we use the QQ-plots Birch-Pagan test to test for heterostochasticity and the Shapiro test for normality to verify if it is suitable. For the random forest, it builds a forest of decision trees and combines the results to make better predictions. The predictions are based on the average of all the tree predictions. And then for the k-nearest neighbor, it predicts a value of averaging the target values of the k closest points. And the predictions are based on the average of the neighbor's values to test for similarity.
For our model performance, we looked at R squared and root mean squared error. R squared being the proportion of the variance in the dependent variable that's predictable by the independent variables. It tells us how well a regression model explains the variability. It's used to evaluate the accuracy. The closer to 1, the more accurate it is. Root mean squared error measures the average magnitude of errors between the predicted and actual values. It tells us how far off the model's prediction is. Error is the same in units as the dependent variable, which is minutes. Better performing model has higher R squared and lower RMSE values. Results: multiple linear regression. The Birch-Pagan test shows presence of heteroscedasticity. The Shapiro-Wilk test shows lack of normal distribution, indicates a nonlinear model would be better suited for R data. K-nearest neighbor and random forest. Random forest had a higher accuracy score and lower error range. Our results are shown in the table below.
So for each of the models, we had plots inserted here to view. For our LMR-QQ plot, as we can see on the right, the residuals are not normally distributed based on this QQ plot, and there are signs of heavy tails and left skewedness. For random forest, we have a scatter plot. Here we have most plots fall on the diagonal line where y equals x, and the model's predictions are well aligned with reality. Our K and N scatter plot is similar to our random forest, where the points fall on the diagonal line as well, but it is not as close of a fit as random forest.
In conclusion, overall, after observing the three models, multiple linear regression, random forest, and k-nearest neighbor, we have concluded that the best fit model to predict delays in this random forest. Some highlights. The project aims to formulate a perspective on flights delays using schedule times to accurately forecast delays. Best model. Random forest was able to give us the R square of 0.937, meaning it is the best model. Closer to 1 is the most optimal. We have concluded that the estimated delay time is roughly 15 minutes. The K nearest neighbor delay would be 30 minutes. These are our following references.